Second law of thermodynamics. All right, there's three laws of thermodynamics that we're going to look at. The total energy of the universe is constant. That means that energy is not created, just destroyed. It's just transferred from one form to another. Um, Second law of thermodynamics, the entropy of the universe increases in a spontaneous process. So what goes into the universe? Well, the system and the surroundings. All right, so if you add those two things together, you get everything. So the system is what we study, right? The chemical reaction, the surroundings is everything else. And as long as you add those two things together, the change in the disorder of the system and the disorder of the surroundings, as long as that's greater than 1, you'll have a spontaneous process. So we need to know how to consider the system in reference to the surroundings. I mean, we can't measure how disordered the surroundings becomes, right? It's the whole everything else. So there's got to be a way of referencing the system against the surroundings. All right, with entropy changes of the system, if it's a positive value, when you look at the change in the entropy of the system, that means you're becoming more disordered. If there's a negative sign with the system, it means you're becoming less disordered, more ordered, implying a non-spontaneous situation, less probable. All right, we can look at the tables, right? We can look at how disorganized something is in comparison to something. So what are we comparing where there's no disorder? And that's the third law of thermodynamics. So again, we sum up the delta S's or the S's of the products, subtract it from the sum of the S's of the reactants, and we get the change in the entropy, how disordered something becomes. We can make a good guess as to how disordered something becomes. We look at whether gases are being produced or lost. All right, so we can calculate the standard enthalpy change for this reaction, or we can look at the fact that, hey, if you want to figure out whether it's a positive value or not, we're losing gas. You got 4 moles of gas going in, 2 moles of gas coming out. That implies we're going to have a negative value in disorder. We're losing disorder. So if you're losing gas, you're losing disorder. So 2 moles of gas on the right. Oh, 3 moles of gas. I'm sorry, I had 4. So 3 moles of gas on the left, 2 moles of gas on the right. So this implies you're losing disorder. So if a reaction produces gas, you can depend on it being a positive value for the S of the system. If a reaction produces no net change in gas molecules, the delta S could be positive or negative, but what we do know is that it's going to be small. So if gases aren't involved in the process, you could become disordered more or less disordered, but you do know that you're not going to have a big entropy change. So a general rule, a reaction that increases the total number of molecules or ions, you're increasing disorder. So if you have particles, more particles being created during a reaction, chances are you're becoming more disordered. So back to our situation, right? We've got 3 moles of gas going in, 2 moles of gas coming out. We already know that the sign on delta S is going to be negative. We're losing disorder. So I can look up on a table what the S of formation is for carbon monoxide and the S of formation is for oxygen at standard state. Hey, notice for oxygen, whereas with delta H's we just arbitrarily decided that they were going to be 0, there is a disorder measurement for elements in their standard state. So we look these up, multiply them by the coefficients. We look up the S of formation for CO2, multiply it by its coefficient, and then subtract reactants from products to get the change. So as we predicted, it was going to have a negative sign. So we're losing disorder during this process. Like I said, where is there a place in the universe where there's perfect order? The answer is at 0 Kelvin. So at absolute 0 Kelvin, minus 273 degrees Celsius, this is the point where there's considered no more molecular motion and therefore perfect order. So 1 Kelvin, you're becoming more disordered compared to 0. 2 Kelvin, you're becoming more disordered and more disordered and more disordered. So we can go back to that point at absolute zero, where we consider it to be perfect order. So there's your how disordered you are as compared to 0 Kelvin. All right, entropy changes with the surroundings, right? So we have to have a way of referencing how the system's changing and versus what effect it's having on the surroundings. So entropy changes in the surroundings. How are the surroundings affected by cooling? Exothermic reactions increase the entropy of the surroundings. All right, so if the system is losing heat energy to the surroundings is becoming more disordered. If you've got an endothermic reaction, the surroundings is losing heat to the system, so heat's going into the system. That means the surroundings is cooling down and the surroundings is becoming more ordered. So that's how we look at it, right? If you increase the temperature, becoming more disordered. If you're decreasing the temperature, you're becoming more ordered. So the relationship between the delta S of the surroundings, how disordered the surroundings coming versus the system, is you have a negative sign, and that implies that's an inverse relationship, right? If the system is losing heat, the surroundings is becoming more disordered. If the system is gaining heat, the surroundings is becoming more ordered. And so negative delta H divided by absolute temperature is equal to the delta S of the surroundings. So this is how we reference the system with the surroundings. So the system loses heat to the surroundings becomes more disordered, right? Entropy increases. If the surroundings is losing heat to the system, well, the surroundings is cooling down and you're decreasing the entropy of the surroundings. So when the delta S of the surroundings is positive and the delta S of the system is positive, when you add these together, you get a spontaneous process. When the delta S of the system is negative, right, you're losing disorder, and the surroundings is losing disorder, that means the universe is losing disorder, so not spontaneous. When the delta S of the system is positive and the surroundings is negative, or the delta S of the surroundings is positive and the system's negative, it'll depend on the magnitude, how disordered the surroundings is getting compared to the system, or how disordered the system is getting compared to the surroundings. So we don't know whether it's spontaneous or not. We'd have to reference the system versus the surroundings. All right, spontaneity and temperature. A reaction can be spontaneous at one temperature and non-spontaneous at another temperature. So again, right, what's going on with the universe? Is it becoming positive or negative? So we can't look at how disordered the surroundings is coming, but we can equate the surroundings to the system by using negative delta H of the system divided by T. So we can plug that into the equation for the second law of thermodynamics, and we rearrange it. All right. So right now we have the delta S of the universe is equal to negative delta H of the system divided by T plus the delta H of the system. If we divide both or multiply both sides by T, we get the delta H of the universe times T is equal to negative delta H of the system plus TS of the system. And if we multiply both sides by -1, we end up with negative delta S of the universe is equal to delta H of the system minus T delta S of the system. And this is what we call the equation for Gibbs free energy. So negative T delta S of the universe is synonymous with what we call delta G, Gibbs free energy. So Gibbs free energy is equal to delta H of the system minus T delta S of the system. So we're referencing the system in both situations. So what's going on with the disorder of the system? What's going on with the delta H of the system? You put the two things together and you can figure out whether you're spontaneous or not by looking at the sign on delta G. Delta G is a measure of energy. It's measured in joules. So if you are releasing free energy, meaning you have a negative sign on delta G, that means the system is going to a more stable state and you are spontaneous.